We're going to look at the Chatelier's principle, which describes the effect of changing conditions on the position of equilibria of a reversible reaction. We're then going to apply the Chatelier's principle to a number of different questions using some key phrases to help us explain the effect of changing conditions on the position equilibrium. We're also going to look at the effects of adding a catalyst to the position equilibrium. Le Chatelier's principle states that if a condition that can affect the position equilibria is changed, the equilibrium will shift or move to oppose the change made. So what does that mean? One way to explain this is to use an example. So if I've got an equilibrium mixture and I raise the temperature of this equilibrium mixture, let's say I've got the mixture in the Haber process, which are a mixture of three gases to make ammonia, and I raise the temperature of this mixture. If one of the reactions, either the forward or reverse reaction, is able to absorb the added heat, then that reaction will speed up compared to the other reaction. So temporarily there won't be a dynamic equilibrium because the rate of the forward reaction and the reverse reactions are no longer equal. So in this case, which reaction, either the forward or reverse, would absorb the added heat and therefore would speed up compared to the other, and therefore what we call would be favoured. So would it be the exothermic reaction, which releases more heat and raises the temperature, or would it be the reverse reaction, which absorbs the heat and lowers the temperature again? Well, hopefully you can work out that it is the reverse reaction that will absorb the added heat. So the reverse reaction is favoured. So as we said, what that means is that the reverse reaction speeds up compared to the forward reaction temporarily, and we don't have a dynamic equilibrium anymore until the original conditions are restored or as close to being restored, and we reach a new position equilibrium. So in this case, if I raise the temperature of this reaction and the reverse reaction is favoured to absorb the added heat, the position equilibrium will shift to the left hand side as we produce more of the nitrogen hydrogen and use up more of the ammonia. So this will decrease and this will increase. So the position equilibrium will shift to the left hand side. Just a bit of a side note, you may have noticed that the forward reaction is the same value as the reverse reaction but the opposite sign. So this is a bit of a revision then of Hess's law. So going against the flow of this arrow, going this way, we switch the sign. So what I'm going to do now is give you some steps to help you answer questions on the Chatelier's principle and working out the shift in equilibria for the changing conditions of a equilibrium mixture. So the first step you would think of doing is to work out and state and say which reaction, whether it's the forward or reverse, that is favoured. So if you raising the temperature, which one of those reactions could lower it? Or if you raise the pressure, which one of the forward or reverse reaction can lower it? If you lower the temperature, which one of the reactions would raise it? Or if you increase concentration of one of the reactants, which one of those reactions would decrease concentration? So which one would oppose the change you make? Which one would therefore be favoured or preferred? So next thing you're going to do is describe which direction, or either left or right. So you got left or right side of the equation. The equilibrium will shift or shifts to oppose the change. So you need to say to oppose the change. They will look for this in the mark scheme. So I'll do some examples of these questions with you in a bit. And lastly, they do ask you to describe what happens to one of the properties of this mixture, like the concentration of one of the reactants or the appearance, like a colour change or something like that, then you need to say that as well. So if needed, describe changes in amounts, so moles or concentrations, or appearance, So it could be a colour change. I'll do an example of that with you later, etc. Asked for, so if they ask for it. So let's apply those steps then to some questions. So here's an example. We've got a mixture of gases and we're converting the sulfur dioxide here by oxidizing it to give us sulfur trioxide. And this is actually called a contact process, which is the first step to make sulfuric acid. Now, we often write the enthalpy change for the forward reaction next to the equation for an equilibrium. So this forward reaction is exothermic, and therefore, according to Hess's law, the reverse reaction will be plus 189, so that reverse reaction will be endothermic. And the question asks us what happens to the concentration of the sulfur trioxide if the temperature is increased. So let's look at what happens. Well, the forward reaction we know is exothermic, so favouring the forward reaction will release more heat and raise the temperature. Going the other way, favouring the reverse reaction, which is endothermic, will absorb added heat to lower the temperature. Well, we have increased temperature, so this will favour the reverse reaction, which absorbs that added heat to lower the temperature again. So what will happen to the concentration of sulfur trioxide if the reverse reaction is favoured? Well, the concentration of sulfur trioxide will decrease as it's reacted away. So using the steps I talked about earlier, so let's describe what happens to this reaction if I raise the temperature. So if we raise the temperature, the reverse reaction is favoured. So the equilibrium will shift to the left-hand side to oppose the change. And because we asked what happens to the concentration of sulfur trioxide, we will say, and the concentration of sulfur trioxide will decrease. Let's look at temperature again, but for a different reaction, and it's one we've already seen before. Here we've got dinitrogen tetroxide, N2O4, which is colourless, and we've got nitrogen dioxide here, which is brown. And the enthalpy change, which is always written for the forward reaction if it's written next to it, is endothermic for the forward reaction. So therefore the reverse reaction is going to be minus 57.2. So the reverse reaction is exothermic this time. And the question says the temperature of the mixture was changed and the colour of the mixture became paler, so it's losing its colour. Explain whether the mixture is heated or cooled to cause this change. Well, look at the evidence here. If it's going paler, we're going to remove the nitrogen dioxide, so the equilibrium is shifting towards the left-hand side to produce more of the colourless dinitrogen tetroxide. So the reverse reaction is favoured. Well, we're told that the forward reaction is endothermic, so therefore the reverse reaction is exothermic. So the reverse reaction is releasing heat. So to oppose the change by releasing heat, the change must be decreasing the heat. So we must be lowering the temperature in order for the exothermic reaction, the reverse reaction, to be favoured. So we have cooled the mixture to cause this change. So using the key phrases I talked about earlier, let's explain our answer. So for the reaction to become paler, the reverse reaction is favoured. So we're removing the brown nitrogen dioxide, so the reverse reaction is favoured. So the exothermic reaction was favoured, so we said the reverse reaction was the exothermic reaction. So the exothermic reaction was favoured to oppose the change. Because we were asked whether the mixture was heated or cooled, we're going to say therefore the mixture was cooled to favour the reverse exothermic reaction. So we've done a couple on temperature changes. Let's look at a different condition. So let's look at effects of concentration on the position equilibrium. So here we got the formation of an ester from an alcohol and a carboxylic acid, and we do this reaction in the second year where we look at it in more detail. So the question says what happens to the yield of ester if the concentration of the ethanoic acid is increased. So we want to know what happens to the concentration of this if I increase the concentration of this. Well, according to the Chatelier principle, increasing the concentration of the ethanoic acid here will favour the forward reaction to remove it, to reduce it again. So the forward reaction will be favoured, and therefore the position equilibrium will shift to the right-hand side. So the amount of ester, or the concentration of ester, would go up, will increase, and therefore the yield of the ester would also increase. So increasing the concentration of the ethanoic acid would favour the forward reaction, and the equilibrium will shift to the right-hand side to oppose the increase or oppose the change. So the yield of the ester will increase. So let's look at a different type of question, but on the same equilibria. So here we've got the same reaction, which is the formation of the ester from the alcohol and the carboxylic acid. And the question says, what happens to the yield of the ester if some alkaline is added to the mixture? Well, we haven't got any alkaline in any of the reactants or products, so what's going on here? We've got an alcohol, we've got a carboxylic acid, we've got the ester, which is not an alkali, and we've got water. So what can be going on? Well, think about which one of these substances will react with an alkali. Hopefully you will guess that is the carboxylic acid that will react with an alkali. So think about what happens if you add an alkali to this mixture. Well, if it's going to react with the carboxylic acid, the acid is going to be reacted away. So effectively what we're saying here is we are decreasing the concentration of the carboxylic acid by adding the alkali. So if we decrease the concentration of the carboxylic acid by adding the alkali, because the alkali is removing it, the equilibrium will shift to the left-hand side to replace what we lost. So the reverse reaction will be favoured to replace the carboxylic acid that was removed by the alkali. So therefore the yield of the ester would decrease, as this is going to break down to form more of the acid to replace what's been removed. And at the same time, incidentally, it will produce more of the alcohol as well. So let's first say what we've done to the mixture. So the added alkali will react with the ethanoic acid and decrease the concentration of the ethanoic acid, or CH3COOH. And the reverse reaction will be favoured to replace the removed acid. So the equilibrium will shift to the left-hand side to oppose the decreasing ethanoic acid, or CH3COOH, or oppose the change. Because we asked about the yield of the ester, we're going to say, and the yield of the ester decreases. So we covered the effect of changing temperature on the position equilibria, and also we covered the effect of changing concentration on the position equilibria. We're now going to look at the changing pressure on the position equilibria. So according to the Chatelier principle, an increase in pressure applied to the equilibrium mixture will lead to the equilibrium shifting to oppose the change by decreasing the pressure itself. So we need to know what reactions decreases the pressure, and also what reactions will increase the pressure if we happen to decrease the pressure of a reaction mixture. So from GCSE you may know that the equation for pressure is force divided by area, or force over area. Simply put, if a force acts over an area of a surface, we produce a pressure. So gas particles colliding with the inside surface of the container walls produces the forces acting over the area of the container walls to produce a gas pressure. The more gas particles there are inside the container, the more collisions or forces acting on the container walls there will be, and so will lead to a greater gas pressure. Reactions that lead to an increase in number of moles of gas particles will lead to an increase in pressure, and reactions that lead to the decrease in number of moles of gas particles will lead to a decrease in pressure. You must include the word gas in your explanation for the change in pressure, otherwise you lose the mark in exam. So for example, if you look at the Haber process again, the forward reaction will produce fewer moles of gas particles, so increasing the pressure will favour the forward reaction. So in this case you can see the number of atoms in total are the same on both sides, but reacting forwards will give us fewer molecules, so we have fewer particles in total in that container, so therefore there'll be fewer collisions with the container walls in a given time, leading to a lower pressure. So if you just say that increasing the pressure favours the forward reaction to produce fewer moles of particles and therefore reduce the pressure, that won't be accepted in the exam for the mark. You must include the word gas, otherwise you don't get the marks. So you must say something like this: increasing the pressure favours the forward reaction as it produces fewer moles of gas particles. The word gas must be in your answer, and that's the most common mistake people make. They leave it out. So changing pressure only affects the position equilibria for gaseous reactions, so it won't affect reactions without any gases. And even then, some reactions involving gases will not be affected by pressure, as you will see later. So let's look at a couple of questions involving gas equilibria and see how we can apply the wording we learnt earlier to these questions. So here we got an equation which describes what we call synthesis gas, which is a method of making hydrogen from natural gas. There's actually two steps in the industrial process, but I'm going to look at the first one here. So we're converting methane and steam to hydrogen gas and carbon monoxide. And the question says, what happens to the yield of the hydrogen when the pressure of the mixture is increased? So if we look at the mole ratio of gas in the equation, there's 2 moles of gas on the left-hand side of the equation and 4 moles of gas on the right-hand side of the equation. So if the equilibrium shifts forward, we'll produce more moles of gas in total, and if the equilibrium shifts to the left-hand side, the moles of gas in total will decrease. So as we said, if the equilibrium shifts forward, in the mixture of all 4 gases, we're going to get more of these. Converting these gas particles to these gas particles, we'll get more gas particles in total. So therefore the pressure should increase. So if we apply a pressure increase to the mixture, it will favour the reverse reaction, because the reverse reaction will produce fewer moles of gas in total. So in that container there'll be fewer particles of gas colliding with the container walls, and therefore reduce the pressure to counteract the increase in pressure you apply to it, to oppose the change you apply to it. So according to Chatelier's principle, increasing the pressure will favour the reverse reaction that produces fewer moles of gas. So the position equilibrium shifts to the left-hand side to oppose the increase in pressure applied, and the yield of hydrogen gas decreases. In this question we got another gas equilibria. On the left here we got a colourless gas, hydrogen iodide, and it decomposes to give us hydrogen gas, which we know is colourless, and iodine we know is a violet solid that vaporises very easily. So when hydrogen iodide decomposes, unless it condenses onto a cold surface, we get a lot of the iodine vapour. So this is why I've written the gas for the state symbol iodine. But as you know, iodine is a solid at room temperature pressure that sublimes at relatively low temperature to give a gas. So the question says, what happens to the depth of colour of the mixture if the pressure of the mixture is increased? Well, the only thing here that gives a colour is the iodine, so we want to see whether we're going to get more iodine or less iodine if I increase the pressure. So looking at the mole ratio of gases, on the left hand side we've got 2 moles of gas particles, on the right hand side we've got 2 moles of gas particles. Moving forward in the reaction, we don't increase or decrease the number of moles of gas particles, and the same going the other way. So changing the pressure in this case will not affect the position equilibrium. There's no effect. So even though there are gases involved in this reaction, it's not affected by changing pressure. So according to the Chatelier's principle, increasing the pressure will favour neither the forward nor the reverse reaction. So the position equilibrium does not change, and the appearance or the depth of colour of the mixture remains unchanged. We looked at a number of different conditions that may affect the position equilibria, like temperature, concentration of solutions and pressure of gases. Now I'm going to look at what happens if you add a catalyst to an equilibrium mixture. Will it affect the position equilibrium? Well, the answer is no, and you can see this on the energy profile diagrams. When you add a catalyst, it lowers the activation energy of a reaction. So on the left hand side here, we've got the energy profile for the Haber process. So here's the original uncatalyzed activation energy of the reaction for the forward reaction. If I add a catalyst, the activation energy lowers from this point to this point. So now this is the activation energy for the forward reaction. It is smaller, so therefore a greater proportion of particles can exceed the activation energy at any given time, so the rate of the forward reaction would increase. On the right hand side we've got the same diagram. All I've done differently is labelled the activation energy for the reverse reaction. So like the forward reaction, activation energy always starts from the reactants, so in this case it would be from the ammonia, and the arrow then points to the line for the activated complex or the intermediates. So by adding catalysts, I've lowered the activation energy for the reverse reaction as well. So this would increase the proportion of ammonia particles that can exceed the activation energy for the reverse reaction. So a greater proportion of particles can exceed the activation energy in any given time. So therefore the reverse reaction will increase in rate. So in a dynamic equilibrium, a catalyst increases the rate of both the forward and reverse reactions equally. Therefore neither the forward nor reverse reactions are favoured, because we've increased the rate of both the forward and reverse reaction equally. So there's no effect on the position equilibrium if you add a catalyst to a reversible reaction. However, what does change is that equilibrium will be reached much quicker as you've increased the rate of the forward and reverse reactions equally. So we covered the effect of changing conditions on position equilibrium, and we explained it in terms of different key phrases and key words. We've also looked at the effect of catalyst on position equilibrium, and there's no effect on the position equilibrium, but it will increase the rate at which equilibrium is reached. In the next video, we're going to combine the topic of rates of reaction and this topic of equilibrium and apply it to setting suitable conditions for different reactions in industry.